Hello and welcome back. In this video, we'll be looking at some examples of converting from decimal to binary, as well as some examples of converting from binary to decimal. If you're not sure what the difference is between decimal and binary numbers, or you're a little bit practiced in remembering what we did in grade 10, please refer to the binary conversion video that is also uploaded to this channel. So when we're looking at decimal to binary conversion, we're going to start by looking at binary to decimal, and then we'll move from there. So if we have a binary number, let's say we'll make an 8-bit number, a nice simple one. Okay, we know the value of each of these digits is a base 2 value. So in this case, it's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. I'm not going to actually write all those in because I don't really care that they're 2 to the 0 to 2 to the 3. What I'm going to do is I'm going to look at the actual values of that. So 2 to the 0 is 1, 2 to the 2 is 2, or 2 to the 1 is 2, sorry. 2 to the 2 is 4, 2 to the 3 is 8, and each time we're just multiplying by 2. So I'm just going to continue that pattern. 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, and 64 times 2 is 128. So we have 8 bits and we know the value of each. In this case, we have a nice easy example because the only 1 bit that we have is that first bit. It's the 128 bit. So we know we have 128 times 1 plus 64 times 0 plus 32 times 0 plus 16 times 0 plus 8 times 0 plus 4 times 0 plus 2 times 0 plus 1 times 0. Now, those of you who are fairly clever realize that this whole piece of the thing doesn't really matter because those are all zeros. So this number is, in fact, the equivalent of 128 base 10. In fact, anytime we only have a single digit, it's the equivalent of what's above it. So if we were looking at the number 64, 0, 1, 0, 0, 0, 0, 0, 0, only the 64-bit is active, which means that this is a 64 in base 10. If we have 0, 0, 0, 0, 1, 0, 0, 0, only the 8-bit is active. Probably shouldn't call that 8-bit because it is the bit with the value of 8, but the whole number is an 8-bit number. Okay, so in binary, this number is equivalent to an 8 in base 10. So this is quite simple when we're looking at it with a single binary digit, pretty easy to do math. So let's try adding in a second binary digit. So we'll start with that one we had just previously, 0, 0, 0, 1, 0, 1, 0, let's say. So most of the numbers the same, except we've changed this single bit here. So when we're looking at this, we know the value of this column is 1, 2, 4, 8. You can continue writing them in when you're getting started, so as you're learning. Once you get a little bit more practiced, you don't need to be writing them in every time. So if we're looking at this, we can say, okay, we have an 8 and we have a 2, right? So we're looking at this bit and this bit, because those are the only bits that are on. If you want the mathematical reason for this, it's because actually to calculate this value, we would do 128 times 0 plus 64 times 0 plus 32 times 0 plus 16 times 0 plus 8 times 1 plus 4 times 0 plus 2 times 1 plus 1 times 0. So if we're looking at this value, we're really seeing the only times we're multiplying by a 1 are those two cases, and all these other cases are just going to evaluate to a 0. So there's not really a point in including them. So if we get 8 plus 2, I'm going to write it back up here. The base 2 number is equal to 10 in base 10. Didn't really mean to pick one that was 10 in base 10. So if we add in a third digit, it's basically the same system every time. So let's say we go back to our old friend 128. So now we've added one extra digit again. This first digit is now a 1. And we're going to say, okay, now these digits are worth 1, 2, 4, 8, 16, 32, 64, 128. Like I said, when you get started, you're going to find yourself writing these numbers in quite often. And there will be a video later on how to use the Windows calculator in programmer mode to switch between binary and hexadecimal and denary or decimal. But in this case, we're just working on this practice because honestly, once you get good at this being able to do the binary to decimal conversions and the decimal to binary conversions is just going to make everything else you're doing with subnetting networks much quicker. So if this is a base 2 number, then our decimal number is going to be 128 plus 8, I'll make those arrows, plus 2, which gives us a total of 138. So this value is 138 in base 10. Okay, so I'm going to give another example here. This one is going to be, let's say, 0, 1, 0, 1, 1, 0, 0, 0. So still 3 bits that are 1s. I'll even write the numbers in like this for you, 2, 4, 8, 16, 32, 64, and 128. And what I'm going to do here is I'm going to suggest that at this point, you pause the video, you wait a couple, or you attempt this yourself, figure out what the decimal value is in base 10, and once you've calculated the decimal value in base 10, then restart the video, and you'll be able to follow me through the process. Just giving a little bit of time for those people who maybe haven't got to pause yet. Okay, so I'm going to restart now. So hopefully you've paused and you've solved out this question yourself. So I'm going to go through it fairly quickly, but I am still going to go through the process. So here we see that the digits we're looking at are a 64, a 16, and an 8. So we can just add those together. 64 plus 16 plus 8. And when we add those together, we're going to find that we get 18, 1 and 6 is 8. So this digit is in fact 88 in base 10. So you can check your answer against this answer and see if you have a clear understanding. At this point, I'm going to move into converting the other way so this is binary. So we're starting in base 2 and we're moving to base 10. Now we're going to do it the other way. So we start with a decimal number and we move to a binary number. So I'm just going to give myself a little bit more space to work here. So if we have, let's take actually this last example we did, 88. So if we have a decimal digit 88, so 88 base 10, and we want to convert it to some binary digit base 2. What we're going to have to do is we're going to look at the values of the binary digits, and then we're going to decide based on these values which ones we need to incorporate in order to build this number. So to start off with, we look at the 128. Do we need a 128 to add up to get 88? Well, 128 is larger than 88, so we're probably not going to have 128 as a part of 88. So I'm going to say no. Could we use 64 to build up to 88? Well, 64 is less than 88, so yes, we're going to use that digit. So now we have left over 88 minus 64, which leaves us with 8 minus 4 is 4, and 8 minus 6 is 2, 24. So now we're trying to build up the rest of this number. So we say 32. Okay, do we have 32 things left? Could we add 32 to 64 to get 88? No, we would get too big of a number. Could we add 16 to 64 to get 88? Well, we could definitely, it would be part of it. So let's add that 16 in there. So now we've removed 16. Okay, so we have 14 minus 6, which is going to give us 8. Sorry, I'm running out of room here. Okay, so 14 minus 6 gives us 8, and 1 minus 1 gives us 0. So we have 8 numbers left. So are we going to use an 8 to add up? Of course we are. It's going to finish up our whole number. Okay, and then now 64 plus 16 plus 8 is 88. So we can just fill in the rest of the values with 0. So 0, 1, 0, 1, 1, 0, 0, 0. I'm going to move my little base 2 symbol over here. So that's our base 2 number. And if we go back to the previous example, we can see we got the same value. Of course we did. We went from binary to decimal, and from decimal back to binary. Makes sense that we wouldn't have any issues. So I'm going to do one more quick example from decimal to binary. And again, this time I'm going to suggest that you pause the video once we have it started. So if we're looking at the value of, say, 192 in decimal converted to binary. So pause now. and then attempt the question yourself. And when you're ready, hit play. So at this point, I'm assuming that you've already attempted this question, so I'm going to go through and I'm going to convert this to binary so that you can check your answer. So I've already written out the values of the binary digits so that it's easier for me to do my calculation. Quite often if you're working on a whiteboard, I recommend that you just leave these values right at the top of your whiteboard and don't erase them, and just erase the values you're working with. Okay, so we're looking at 192. We're going to look at the first value, the largest value, which in this case is our 128, and we're going to say, okay, to get to 192, should we use 128? Doesn't make sense? Well, yes, because 128 is less than 192. So in this case, we're going to use that digit. So we get 192 minus 128 leaves us with 64. So we go to the next digit. So when we're looking here, we say, okay, are we going to use the 64? Well, we still have 64 left, so yes, we're going to use that digit. Now we have no values. We've actually already totaled exactly 192, so at which point we're just going to fill zeros into the remaining digits, and our final binary digit is going to be 11000000, base 2. So you can see that 192 is quite common, but also it's a fairly simple calculation once you know that it's the first two digits there.